What is up, you guys? Welcome to the second lecture of this series entitled Machine Learning with TensorFlow and Scikit-learn. In this one, we'll be introducing you to binary classification and a way to solve this problem using the Stochastic Gradient Descent Classifier. We'll be seeing how to set up JUPYTER Notebook for dealing with classification problems, and in particular we'll be dealing with the MNIST Handwritten Image Database. And so after formulating the binary classification problem, we'll see a way to solve this problem using the SGD classifier. Not only are we going to show you how to implement the SGD classifier on sklearn, we'll also show you how SGD mathematically works. We'll be seeing different loss functions as well as penalty functions, their interpretations, what they mean, so that you get some intuition on how the SGD classifier works. So without further ado, let's get started. Right, so now we're going to talk about classification in machine learning. But before we do that, we'll be talking a bit about a very important data set that is the MNIST, right? Which stands for the National Institute of Standards and Technology Database, which is a large database of handwritten digits that is commonly used for training various image processing systems, right? Pretty well known in machine learning, and it is often referred to as the hello world of machine learning. So as you can see over here, we've got samples of handwritten digits that are used to train usually classification algorithms. So if you have a new classification algorithm and you're really curious how it works in practice, well, the first data set that you should be thinking about is this one over here, okay? We'll be working with this data set throughout the coming lectures that have to do with classification methods. And just a small remark here, the size of this data set is something around 70K. So we've got 70K small images. Each one is a grayscale image, and we'll see what it means to have a grayscale image. How do we process it? It's really simple. And it consists of, as I said, digits written by more or less high school students and employees of the US Census Bureau. And as you can see, for example, if we're training the model for digit 0, we've got many shapes and forms for zeros. The more, the merrier, right? Because we'd want the machine to recognize all handwritten zeros, right? So throughout this course, I'll be working with JUPYTER Notebook on Google Chrome, and the way you can set it is by opening a terminal, right? Next, you choose a certain path and you just cd to it. Then you type in JUPYTER Notebook. If you don't have it, go ahead and install it using pip3 if you're using Python 3, or just pip install JUPYTER. Nah, that's not how you write it. The way to write it is as such. Now, since I have it installed, this doesn't take any time, but if not, just give it some time. Go grab a coffee, then come and check back after like 5 or 10 minutes, depending on your internet connection. Now that everything's good, let me clear everything out and type in JUPYTER Notebook. As you can see, I'm on a Google Chrome, and the notebook will be running using your local host. So click on New Python 3, then I'll call this one classification such. Okay. Now to fetch your data, we're going to use sklearn, and in particular OpenML for that. Let me show you how. So from sklearn, and again, if you don't have sklearn, you open your terminal. Now you don't close this instance of the terminal because JUPYTER Notebook is using this kernel over here. You open a new terminal, you type in pip3 install sklearn in case you don't have sklearn. Since I have it, all is good. If not, again, have another cup of coffee and then check back later. Now, assuming you have sklearn, go ahead and import from sklearn the fetch underscore OpenML as such. Now, it's not sklearn, it's the data sets in sklearn, right? There you go, it's working. And the next thing I want to do is read the MNIST data using fetch underscore openML. The data I believe is called MNIST underscore 784. Okay, run this to make sure. I'm going to take some time because the data set is big and this is performing HTTP requests. So the function fetch underscore openML is written using HTTP exchange function. Now it compiled means that we've got the MNIST. There you go. As you can see, it's messy. We're not going to work with this version because it's super messy. We need to pre-process this data set a bit before working with. So for that, I'm going to first convert the MNIST data to, or more formally, I'm going to cast it as an int 8. Now, as you can see, I'm calling this again, which is bad. So I should write this on a new cell over here, right? We don't want to repeat this because this requires a lot of time. And once executed, I know that I have the MNIST data with me, right? So allow some time so that this finishes. And again, NP is not found. So we need the NumPy. From NumPy, or just import NumPy as NP. Now, what is NumPy? NumPy is the fundamental package for scientific computing with Python. It contains, among other things, following sophisticated functions. I've got the following NumPy tutorial on YouTube. I'll leave the link for this in the description below. It basically teaches you everything you need to know about NumPy, from setting up JUPYTER till all the main functionalities, or most of the main functionalities that NumPy is capable of doing. Okay, so let's run again, and then we won't touch this anymore, right? Because we know that this takes a lot of time. So this cell, we don't touch it again. Okay, good. So let's run this and check how this data set looks like. Now it contains images in the form of int 8, which is what we want. Let me access the data to show you what I mean. As we said over here, we've got 70,000 samples. There you go. And we've got 784 number of columns. Now, what is 784? Go ahead and perform the square root of 784. You get 28, an integer. So what this basically means is that all the vectors that lie as rows over here, you could form a 28 by 28 matrix using an appropriate adjustment or reshaping, right? And that's how the image looks like. It's a 28 by 28 grayscale image. So going back to MNIST, this looks like a dictionary, and what you see over here is the data field, which could be accessed as we did right here as such, right? Pass it the key. You've got the target that will be the Y values. So this is of size 70K. So per row, we've got a response. The way you should read this X matrix, so this is the X matrix expressed in terms of its rows. So the way you should read it is that each row has a label, right? A label indicating what's the digit of this image. So each row is actually an image and it has a label attached to it. Where's the labels? It's called target. This is the Y vector, right? So the Y vector would look something like this. Per column X, there's a Y. And the range of Y is naturally 0 till 9 because that's all the images that are available in the MNIST from 0 till 9. Because once we recognize that, we can generalize to any number, such as 11,000 or 666 or I don't know what, right? Those are the basic numbers that we need to train our machine on. What else could we read from the data set? Let's see. We've got the frame. We've got the feature names, which go from pixel 1 till I don't know what. Let's read it here. Goes from pixel 1 to pixel 784. So that's the grayscale image, right? Per pixel, each column of X is actually a pixel, right? See what else we have. Got some description. See what the description is. So this is actually describing the data set. So there's the author, Jan LeCun, Corina Cortez, and Christopher Burgess. I hope I pronounced their names correctly. So actually, when you're using this data set, you should cite this link over here, right? This reference, right? They're actually giving a bit of description over here. So they're telling you that you can split this data set into 60,000 examples that are the training set, and 10,000 are left off for the test set, right? And you can go ahead and read. You should use a print here to properly read this. It looks way better. So use a print. There's the authors, the source, the site, blah, blah, blah. And here's a better description of what we were saying. So they're telling you that the images were centered in a 28 by 28 image by computing the center of mass of the pixels and translating the image so as to position this point at the center of the 28 by 28 field. Okay, let's remove this. Now let's put the data into some variables, the x and y. Let me call this lowercase y. Okay, as such. Usually that's how it is in reference. Okay, the way you can do this is, well, x is, as discussed, the data, and y is the target, right? There you go. This is x and this is y, right? Both are int8 variables. So now let's actually take a look at the images, right? It will be more fun and see if their corresponding y is correct, right? Unless there's something wrong with the data set. So to accomplish this, we're going to import the matplotlib. In case you don't have it, again, go ahead here, pip3, install matplotlib. Since I have it, I see this. And if not, you would just wait a bit till it installs. So what matplotlib is it's a comprehensive library for creating static, animated, and visualizations in Python. It's a really cool library, open source, and people use it a lot when plotting, not only in machine learning, also in signal processing, financial studies, and many others. So you first import it, and since we'll be using the pyplot a lot, we'll just give it an alias, call it PLT. Okay, so let's pick a digit let's take a look, for example, at the 40th entry of y. It's digit number 1. So if I go ahead and extract the 40th row of x, which is this row vector. As you can see, it's sparse due to the white space, and it is of size, of course, 784, right? Now we need a 28 by 28 image, and the way you can do this is just reshape it to a 28 by 28 matrix. Now if you take a look at digit, it's a 28 by 28 matrix. Now it's not nice looking at it that way. Just use shape to verify. Okay, now let's plot it. So the way you do so is using plt.im show digit as such. As you can see, this is not what we want because what we have is a grayscale image. So the way to do so properly is to fill in the CMAP field by matplotlib.cm.binary, right? There you go. Now we really don't want this axis over here because it's really not useful for images. It's not going to mean, we don't care about, taking a look at those white spaces. So this numbered axis we don't really care about. So why not turn it off? The way to do this is just set my axis to off and plot.show to get rid of, those numbers. And let's say I didn't turn off my plot, you get the address of the image. So the image is stored at this address of your computer. Well, to get rid of this message, just run plot.show, right? Putting back the axis off, you get the image. So the image is actually number 1. Let's pick another image, which is number 0. Pass it 440 here again. And there you go. This is a 0 with a small imperfection over here, right? And a scratch over here. That's probably a youngster over here who wrote it. So that's a good example to train the machine with imperfections, right? Let's choose something else. Number 8. There you go. Take a look at one more digit. 0. No, let's pick something else. 1. Let's pick else. 1 again. Let's pick 8. Let's pick something else. 7. Pick 7. And there you go. Okay, so now that we have the data set along with the target or the response or the dependent variable, now as the authors recommend, let's split the data set into training set and test set as recommended. So the first 60,000 examples are the training set and the last 10,000 are the test set. So the way we can do this is say xtrain is x. Take the first element until the 60,000 minus 1, because Python starts at zeros and this 60,000 is excluded, right? You also pick the test set to be the other elements, so from 60,000 till the end. And the same thing goes for the response. So train first 60,000 and the test be the last 10,000 as such. Now you could have wrote this in one sentence, in one command as such. So x train, x test, y train, and y test, and pass it the right hand sides the same order. First one, here's the second one, third one, and fourth. Get rid of this and run this. Okay. Now you can also shuffle between the training sets. So this will guarantee that all cross-validation folds will be similar, right? You don't want one fold to be missing some digits and these kind of stuff. Keep in mind that some learning algorithms are very sensitive to the order of the training instances. So if you train the instances in a particular order, the learning algorithm will produce different results to another order. So we say that they're permutation sensitive. So let's shuffle to make sure that such a phenomenon would not happen. The way to do this is, let's first produce a shuffling index to be done by NumPy using random permutation. Now, what does this do? If I pass it 3, let's print it. It produces a random shuffle from 0 till 2. Run it again and again, see different shuffles. Now we need 60,000 of those, right? So this is a random permutation of a vector of size 60,000, right? So I'm interested in the indices, pass it to x train and y train, right? There you go. We have just shuffled our training set. So now let's perform some machine learning methods, and in particular the binary classification approach. So what binary classification is in general is that given, say, data set x containing vectors x1 down till xn and certain binary labels, that's the word here. So your y response does not contain digits as the case here. It rather contains 1, -1, 1, and so on. So it's either a -1 or a +1. It's actually telling you that does this data point x1, is it classified as 1 or -1? So in our particular case, when looking at handwritten digits, we'd want to test, let's say, if a certain digit is, let's say, number 6 or not 6. Is that clear? So given a certain digit, I just want to know for the moment if that digit is 6 or not. Indeed, that doesn't totally solve the multi-level classification problem. That is, you cannot, using this machine learning algorithm that tells you if this is 1 or not 1, or 5, not 5, or 6 and not 6, you cannot identify digits that way. But this is, you're midway there. You can actually segregate. You can actually ask a question. Is this 1 or not? If yes, then you identify it. If not, well, you still have other options to explore, right? So let's start off by this simple way of classification. That is the simplest classification problem, the binary one. So let's say for the moment, I want to train number 6. So I go look for the number 6 in the training data I have. So what I get is an array of true or false, -1 or 1, right? Next, I'll also find the digits in the testing set that correspond to number 6. So as to test my binary classifier. Now, binary classification is also one major problem in machine learning, and hence it has a lot of algorithms that approach it. And one popular way is using the so-called Stochastic Gradient Descent Classifier, also known as SGD Classifier. Now, let's go into the theory of that for those interested in the theory. So SGD classification, what is it mathematically? Well, again, back to the binary classification problem. Now, for those not interested in the theoretical part, it's okay, you can skip this part. And for those who are, you can watch this part. So as we said, we've got a data set X containing the training examples x1 down to xn, right, as row vectors, and their corresponding binary labels in vector y that are either plus or minus 1, right? So the goal here is to learn a linear scoring function. That is, f of x is w transpose x plus b. So in other words, give me a vector of the form xk. So give me a vector that it looks like the rows of x, right? And what this function does is it performs this linear transformation given w and given b, which of course we don't know. That's what we'd like to learn using SGD. So you're taking x, passing it through f of x, right? Thanks to w and b. Then you get a number that is absolutely not plus or minus 1, even though the responses are plus minus 1, and even though you learned the method and figured out w and b, you're never going to get a plus or minus 1 at the output of here. But that's what you want. You'd want to take a decision, either plus or minus 1. Well, one way of deciding is actually taking a look, this is one way, at the sign of f of x. You take a look at the sign, it's actually represented as such. If f of x is positive, you say I'm a plus 1, else I'm a minus 1, okay? So it's a plus 1 if f of x is positive, else it's a minus 1. Okay? In other words, we're taking a hard decision on f of x. So in order to make predictions, again, we need to figure out what the w vector is and what the intercept b is. Well, what stochastic gradient descent does is it computes or estimates w and b through a given loss function, or more generally, it takes a look at an error of the following form. So SGD minimizes the error function that consists of a certain loss function. So it minimizes a certain loss function that models or measures the model's misfit, and a certain regularization term that is also known as the penalty, which penalizes the model complexity. We talked about this in the introduction of machine learning. Sometimes about a certain loss, but to account for overfitting, you'd introduce a certain regularizer or penalty. Okay, we'll talk about different options just now. And you've got the certain loss function that accounts or measures the amount of noise or whatsoever. So you're trying to minimize both at the same time, right? And alpha is actually a certain hyperparameter that measures or tells or reports the compromise between penalty and loss, because the higher alpha is, the more you tend to minimize penalty and forget about the loss. The lower it is, you're doing the other way around, meaning you prefer to minimize noise but to forget about overfitting cases. Alpha positive, and it's a hyperparameter. Now, as we said, there's different choices of the loss function and there's different choices of the penalty function. Those are found based on the data you have, or you can find them through experience, and each have their own theoretical studies, of course. Now, the loss function, you could choose least square. The most common is least square. That is, you take yi minus f of xi all square, right? This is ls least square, one option. Another option is you take the log. Once you do that, that's called logistic regression. And the log loss, or the logistic regression loss, is actually the loss function of the so-called logistic regression, which we will be addressing in future lectures. But for the moment, it's given as such. It's minus log fxi 1, where it's log of 1 minus f of xi. So you can choose your log function to be as such. Also, other options such as, oh, and by the way, least squares, now since we've got a penalty parameter over here, this is also called ridge regression, right? Ridge regression. Or also in optimization, this has another name that's due to one of the first people who introduced regularization to the problem of least squares, called Tikhonov. So it's also referred to as Tikhonov regularization. Okay, of course, Russian. Named after a Russian mathematician, Andrei Tikhonov, who was a Soviet and Russian mathematician known for important contributions on topology, mathematical physics, and What's most important here is ill-posed problems with that have many solutions or no solutions. What's the best way to regularize them? Okay. What other options do we have here? We've got the hinge loss. So hinge is used as soft margin, and it's used in SVMs, support vector machines. It has the following form. It's the maximum between 0 and 1 minus yi multiplied by f of xi. Now, ideally, in the absence of noise, fxi would be yi, right? So in the case of yi equal to 1, then fxi is 1. So this term is exactly 0. And hence you get a 0 loss. Now, let's say in the presence of noise, but not too much noise, let's say yi is 1 and fxi is a bit less than 1. So this guy would be 1 minus something that is less than 1, so something that is positive. Hence, you would have some loss, which is 1 minus that thing. Now, if fxi is much greater than 1, we're sure that, there shouldn't be any loss. That's according to Hinge, because fxi is way larger than 1. So, of course, it won't be a minus 1, right? If it were between 0 and 1, as was the previous case, then, okay, you have the 0, which fits in the middle. Then, okay, maybe a bit of noise pushed it towards above 0, right? So let me draw a figure here to show you what I mean. So this is your 0 over here, 0 level. And ideally, you have your yi that is 1, right? So if fxi is, as we discussed, 1, then we have no loss. Actually, there's no loss over here. And what Hinge says, if your f of x is on top of this, then of course it's not a minus 1. I mean, why would it be, right? Because the noise is pushing it away from 1. I mean, if it's not a 1, it definitely is not a minus 1. It rules out the case where you've got an f of x over here and the noise was way too large to push it on top of 1. That is ruled out in a Hinge sense. So if we're plotting this function, the Hinge function, on scale, so for each class yi, we've got a different function, right? So for the class yi equal to 1, so for yi equal to 1, we're actually plotting f of x versus the loss, the Hinge loss, right? So the loss goes here. That is, in this case, max of 0. For yi equal to 1, we've got a 1 minus f of x. Now, 1 minus f of x is a line passing through those 2 points, 1, 1 over here. And since we're taking the max, then this guy laid over here, right? So in the end, for the class y equal to 1, this is how the Hinge loss looks like, okay? It passes through 1, then it cuts out. It saturates over here. That is to say, again, the interpretation that we had here. The higher f of x is compared to 1, we're going to consider that there's no loss, as long as f of x is larger than 1. Now, if it's smaller than 1, the loss increases linearly as f of x, okay? Now, for yi equal to minus 1, you can easily verify that the Hinge function looks like this, okay? This is max means 0, and then this time 1 plus f of x, okay? So that's about it on Hinge loss. Of course, this is a very big topic and it has really favorable properties such as subgradients and all these cool stuff. I'm not going to talk about them now. I'm going to introduce you to one last loss function, that is the ϵ-insensitive, that is used in support vector regression. So ϵ-insensitive is also soft margin as Hinge, and it actually works a bit like, given an epsilon, I'll give you the cost. So give me a small number and I'll tell you what the loss function is. So that said, I'll give you a loss 0 if the absolute difference between yi and fxi is less than an epsilon, right? Otherwise, if it exceeds this sort of error, then I'll take the error as is and I'll subtract an epsilon. Okay, this is another fancy way of saying if the difference is less than a certain threshold, then set this threshold to 0. If it is greater, just take this error, an absolute value of course, and subtract epsilon. So visually this would look something like this. So for, let's say, yi equal to 1, if I would plot the loss versus f of x, right? If this is 1, the yi, and this is an epsilon over here, and here's an epsilon over here, then the loss is 0. Else, your loss will increase linearly with f of x with a slope 1. Likewise, this thing is actually symmetric, so got the same behavior over here. And for yi equal to -1, you've got the same figure but centered at 1. So you've got an epsilon here, got this guy, then your error symmetric line. Okay? Each and every one of those cost functions has their own characteristics of how to model the error. Some work better with some data, whereas others work better in other types of data. Okay, now let's talk about the penalty over here. Let's give some common penalty choices. But the L2 norm has one choice. That is, for a vector n, you just sum the squares of its entries, wi square, and divide by 4. Once you take the derivative, this 2 cancels out with this 2. You've got the L1 norm as well. So the L1 norm, instead of a squaring, you just take sum of absolute values, right? And last but not least, you've got a mixture of L2 and L1. It's actually known as, has a fancy name, and it's known as the elastic net cost. It's a convex combination of L2 and L1 norms. So you multiply this guy by, I don't know, a beta, so a beta 2 multiplied by the L2 norm plus 1 minus beta multiplied by the L1 norm. Now, if you've been following my convex optimization courses, you've probably seen this somewhere when we talked about convex combination. Okay, so those are all. We're not going to write code to generate each and every loss function. Scikit-learn has those functions already there for you, so you don't have to do the functions that compute quadratic losses or hinge losses or elastic net penalties. No, you just specify them as attributes of a particular function called SGD Classifier. We'll be talking about that just after we introduce the theory of SGD. Okay? So now we have the function, it's in front of us. Given L, given R, the forms after we choose them, and for a given hyperparameter alpha, we can optimize this cost function with respect to W and B, parameters that we need to start learning, right? So how does this work? Well, let's say you're in a 1D case. You've got this simple function f of x. X lives in 1D. It's just a scalar function. For example, I've got 5x squared plus 6, okay? So what stochastic gradient does is numerically compute a minimizer of this function, which is obviously x equal to 0. How does it do that? Well, starting from a point, call it x0, it iterates over the following relationship. So xn plus 1 is xn minus eta multiplied by f prime computed at xn, right? In that case, f prime, you do the math, it's 10x. So all you have to do is just really compute xn minus eta multiplied by 10xn, and there you go. This is your recursive relationship. So starting from x0, plug that in, and given a learning rate, this is called a learning rate, which actually controls the step size and the parameter space. There you go. So start with x0 and you hopefully converge depending on properties of the given function. So the same thing goes for the cost we have here. So if we were to write the same relationship, you'll get something like this. So instead of a xn plus 1, you have a wn plus 1, the w you're trying to estimate, and w transpose xb, right? So your wn plus 1 is updated as wn minus an eta multiplied by the partial derivative of the cost function you're minimizing, EWB, with respect to w and evaluated at wn, right? And your E looks like this. So plugging this in E, you will get wn minus eta multiplied by the partial derivative with respect to w. So first here we had a 1 over n summation of the loss plus an alpha r w, right? Then due to the linearity of the partial derivative, you can go ahead and write this as such. Again, given L, given R, the form of L and R, you can explicitly compute the derivatives. And at a given learning rate, you can update this recursive equation, right? Until conversion. A similar relation could be done with respect to B. Instead, the partial derivative is computed with respect to B, okay? Now, one thing noting about the learning rate is that for classification problems, the learning rate is given as a function of the step size. So at each iteration, we change the learning rate so that it decreases with time, right? That's to take into account conversion. And this was actually a heuristic proposed by Leon Bourteau, where eta n is inversely proportional to a factor alpha multiplied by n0 plus n. And n0 is actually an offset and is determined by a heuristic proposed by Leon Bourteau, who is best known for his work in machine learning and data compression. He worked on the SGD, and I think he's currently working with Facebook, Google Scholar. Yeah, he's with Facebook AI Research. Anyways, here's the paper, which is really famous back at AT&T Bell Labs. This is where he talks about the SGD over here. So this is what we talked about. So a heuristic proposed by Leon was that the expected initial updates over here, the N0, is such that the expected initial updates are comparable with the expected size of the weight. Okay, so this has a lot of impact on the convergence of the SGD. Other related papers that I find myself interesting are papers by also French researchers. Actually, one of them, Eric Moulin, was nearby where I did my master's in Supélec. We just get the paper that I'm talking about. It is this one. So Francis Bach and Eric Moulin are two well-known French researchers that actually did a lot of work on this SGD. Here's the paper, and this work really approximates algorithms for stochastic gradient, because you know the gradient is sometimes not computable. It requires either a lot of computations or approximations to get a closed form expression, because for some losses you cannot compute it. Okay? This paper actually talks about the non-asymptotic regime of such approximation. It has a lot of mathematical stuff which I myself find really interesting. Okay, it could teach you a lot of stuff. Okay, so back to SGDs over here. So this is how SGD works in a nutshell. This is the cost associated with SGD classification, which uses SGD to solve or to optimize this cost. Back to the JUPYTER notebook. So let's say I've got the data that correspond to number 6, and you know, I want to train my classifier. So to go ahead and grab the classifier from the sklearn package, I'm going to point at linear model, because that's the model we're assuming if we were to learn using SGD classification, and we're going to import SGD classifier as such. For that, I'll call a variable, call it SGD classifier, and I'll initialize my classifier object as such. Also, I'm going to fit right now. What do I fit? I'll fit the training data versus y train 6 as such. As you can see, it's taking time. This is not easy. There's a lot of computations going behind the hood. So to limit this, I'm going to go ahead and stop. There you see keyboard interrupt. We can do this by setting the maximum iterations to, let's say, 10. Maximum, we see a warning over here saying maximum number of iteration reached before. So they're telling you to increase the number of iterations. Let's increase it to 20. Same thing. Well, let's keep it 20 and let's set something else. That is the tolerance value. I'll set it to -infinity. Looks good. Okay, so now we've got this object that contains our classifier. It is trained with number 6, with the samples corresponding to number 6. Now, one very important key aspect over here is to check if this classifier is doing a good job. Well, let's call the predict function and see if it's doing a good job. So for that, let's go ahead and try some values, right? So let's go ahead and check y test 6. Actually, let's pick a number at random. So y23. There's an error. Okay, so I think I should pass it as such. So there's a reshaping. Oh, so this is the response. I'm sorry about that. Go ahead and pick a row as such. Okay, and let's reshape it. So reshape 28 by 28. Okay, so reshape your data either using array.reshape. Oh, okay, so the input should be an array of an array as such. There you go. So the classifier classified x1 as false. Okay, now let's go ahead and see what y1 actually is. It's a 0. Good. So at least it shows 0 as not 6. We should give this classifier a reward. It actually did the correct job over here. So let's check 2. 2 is also false. 2, 4. Correct. Now let's actually look for a 6. So 32 is a 6. And there you go. It predicted that 32 is actually a 6. Now, note that we're doing all this on the training data, and it's more fun to see what's going on in the test data because we didn't train the classifier using the test. So for that, we need a performance criterion, right? We need some sort of performance measure that evaluates the classifier because, you know, evaluating a classifier is trickier than doing so for continuous variables, for regressors, because over there, you know, you can just say, oh, I just compute the MSE and this is a metric that reports the goodness of the model. Well, over here it's a bit different, and one way to do so is using the so-called cross-validation. So a good way to evaluate if a certain model is good is to use cross-validation. It gives you more flexibility and allows you to see if your model is actually robust against bad training. Right, so for that, we're going to call sklearn.modelSelection and we'll import the cross-val score. So all you have to do is pass cross-val score classifier and the training set and the test set on 6. Okay, run, take a bit of time. So here the cross-validation score gave you the following. This is actually a score out of 1. How many times it did the job correctly. This is actually a 98.1% correctness on one fold. This is 97.4% on another fold, and so on. If you want to control the number of cross folds, you pass CV, let's say, I'll set it to 4. You will see 4 values just now. And there you go. So with 4 folds, you have an accuracy way above 95%. This is the ratio of all corrected predictions. So this is the accuracy over here. This is what you're seeing, the accuracy. Thanks for watching. If you enjoyed this lecture, please consider subscribing to my channel, liking this video, sharing it on social media. And if you have any questions whatsoever, just leave a comment down in the comment section below. I'll make sure I'll get to it as soon as possible.